Okay, so welcome to my talk. My name is Justus, and I'm going to talk a little bit about virtualization from the Hurd perspective. And let me just quickly introduce the Hurd to you, because I believe a lot of people just know the stupid jokes about it never being done and released. And first of all, what is the Hurd? The Hurd is a general purpose multi-server microkernel based operating system, and the GNU project intended it to be a replacement for the Unix kernel, and as we all know, that didn't happen. But I think there's still a lot of value in the Hurd, because first and foremost it exists and this is highly compatible. So we built on the GNU C library, and we have a fat C library. So most applications just need to be recompiled. Of course, there are bugs and quirks and stuff like that, but it's highly compatible. Also, you got Debian GNU Hurd, so you can install it like Debian GNU Linux, and you will feel at home, I promise. It is also a great place to contribute to learn system programming and maybe to learn how to work in a project or in a GNU project. And I think the most important thing for me was that it freed my mind from a really narrow perspective of what an operating system is and can do for me and for users. And really the Hurd is about the first freedom, the ability to run a program as the user wishes. And it gives me freedom, for example, from my, if I work on a system that I don't control, I'm an unprivileged user. I still want to do crazy stuff on that machine. Or even if it's my own machine, I want to run any program in the environment that I want and I control to a greater extent than it is possible on Linux, say. So what about virtualization? It's everywhere. That's clear. And people do it for different reasons. So maybe they do it for development, or for, the cloud stuff is about maintenance mostly. And some people do it for security. Whatever the reason, virtualization is everywhere. And there are different kinds of virtualization. So you might have whole system emulation or virtualization like Box or QEMU. Or you might want to virtualize just a tiny part of the system. So it differs in grain granularity, right? And back in 2012, I was here and I watched a talk from this Italian professor, Renzo Davoli. If I mispronounce his name, I'm sorry. And he he provided a very general definition of what virtualization is. And he said it's the ability to interpose any resource. And I like that, but I would say it a bit differently. I want to shape the execution environment of my programs in any way I like. This is the point for me, the important point. So we do have a coarse-grained virtualization mechanism in Hurd, and it's subHurds. And it's a bit about like zones or containers or LXC. And what it does, it gives you another view of the system, and you replace the whole system. And it's tricky actually to do this on monolithic systems, because there you have everything or every resource implemented in the kernel. And if you want to do something like containers, you have to introduce namespaces in the kernel. And the Linux community has been doing that for like a decade now. And I'm not even sure they finished. And even if they did, the security of the system always depends on the implementation. If there is a bug, well, you break out of the namespace, I don't know, environment. The nice thing is that it's kind of trivial on multi-server operating systems, because you just have to start another set of processes that implement all the resources. So this is how it looks like to start a subherd. We have this program called boot, and you give it a device, or it could even be a file. And this file contains, or this block device contains an X2 image, for example. And then boot mimics what grub and mark does when starting a real Hurd system. So it loads the initial servers, and it executes this weird scripting language called bootscript. And you can see this here. So we load the file system server, and we pass this pseudo root device to it. This is the thing that's different on real Hurd. And then we load the exec server that executes processes. And then the whole server bootstrap just starts. And what you see here is a screenshot of starting a Debian GNU Hurd system that I installed using deb bootstrap, and I just tweaked it a tiny bit. It's basically the Hurd system runs unmodified inside, and it's just the Debian bits that don't quite cope with the subherd environment, but it works to a large extent. So how does it actually work? Well, we just start another set of servers, like the proc server that implements processes, and the file system servers, and the exec servers. It's a completely separate set. And it actually virtualizes very few things. Most kernel objects like tasks and I don't know, memory management is just used as is. Up to Hurd.09, which we released in December last year, we had to run subherds from a privileged user, that is root, basically. And under this model, the virtualized resources were the console, so that you could see and type stuff, and the root device and the time device. And for the mark device setup, you have this device master port that you use to look up devices. So that was virtualized. So in 2009, we introduced unprivileged subherds, and it was actually not that much to do. So the only thing that was needed is to get task ports for the newly created tasks. Tasks are the mark equivalent of processes. So what was needed is a way to hand task ports to the unprivileged boot process. And we added that, and we now through a mechanism called task notifications, and we added another privileged kernel port stub that we don't have because we are running unprivileged, and yeah, stuff like that. It's actually not a big change. And the nice thing about this boot program is that it's tiny. It's like 2,600 lines of code, which is for a C program not that big. And it actually contains a lot of stub functions and this weird boot script parser thing. So it's quite simple to do coarse-grained virtualization on a microkernel multi-server based operating system. But that's actually not the interesting thing for me, because I want to do fine-grained virtualization. And one central design aspect of the Hurd is that every service is looked up through the virtual file system. So we have the /dev directory containing all the what Unix called device nodes. And in the Hurd, it's nodes, and they are connected to servers. So we've got dev null and stuff, 0, the block devices. And then we have this set of Hurd servers under /servers. Like the crash server, if a process dies, it talks to the crash server and creates a core dump or whatever. And we have the startup server that manages the system startup. And we also got the server socket directory, and it contains our network stack, or network servers. And we don't have a central configuration on how this should look. But what we do is that every node in our file system can contain a translator record, which is basically a command line. And on access, a Hurd server is spawned. This is a bit like socket activation, but more general and in a distributed way, and done in the 90s. So the Linux forks are a bit late. And as an example, this is how our network stack looks like. And showtrans is a program that can query the translator records. And we have this dev netDDE, which is Linux device drivers running in user space. And then we have a simple program, a dev node, for the Ethernet device. And it looks up the Ethernet device through the netDDE driver stack. And then on top I layered the Ethernet multiplexer, which is an Ethernet bridge. And it is connected to the primary Ethernet device. And then finally, on top of all that, we have the Linux TCP/IP stack. And it sits on this node. And it talks to one of the nodes provided by the Ethernet multiplexer. So this is our network stack. So the Hurd uses a terminology. We have a thing called translators. And what is a translator? A translator is a server, and it exposes a certain interface. And why is it called a translator? It's called a translator because it translates between, one domain and the set of virtual file system operations, and maybe more. So the virtual file system operations are described in the file Hurd file system definitions. This is our file system protocol. The Hurd is a set of protocols, and we have a reference implementation. So this is the file system protocol. And there are operations like dir lookup, and you give it a node and a path and a set of flags and maybe a mode if you want to create a file, and you get another node. And sometimes you want to extend this to allow for more operations, because a bit like the Plan 9, we say everything is a file, and then we don't want to communicate byte streams on top of this file system interface, but we have structured data being passed around. And we have RPC definitions to and we get client stubs and server stubs created for it. This is how it looks like if we trace a program. We do stat on etc hostname, and what we see is we send a dear lookup message to this. This is the path and the flags and the mode and so, and we get back another port. Port is a reference to a capability. And as I said, the design aspect is that the virtual file system is used for server lookups, and almost every server in the Hurd is accessible using the virtual file system. And for me, there is this set of underappreciated family of translators. And it's the family of translators that just modify, they map from the virtual file system to the virtual file system. Using that kind of translator, we can modify the view one process has on the system as a whole. So every process has a working directory and a root directory, similar to how it's implemented on other Unixes. And we can manipulate the root directory using settrans, change root. It's not change root in the Unix sense, but it allows us to start a process with the new root directory, and we can provide a server that provides this root directory to the servers. This is how it looks like. So we do settrans change root. We want to execute this command, and we want the root directory to be provided by the remap translator, and we want to remap etc hostname, and we want to substitute it with my hostname, some other file. And then this program is run, and you see not the hostname, but my file. So I successfully exchanged a global configuration file in the Unix way with my own file. And I strongly believe that this is something that I, as a user of a computer, should be allowed to do. And because every server in the Hurd is accessible through the virtual file system, using this very simple technique, we can, for example, replace the server socket 2, which is the network translator for the internet family, with my own server and start some program using it. This way, if my TCP/IP stack uses a VPN, I get all of the network traffic routed through my VPN. And this is on a per process base. So this is a very powerful way of doing virtualization. So I played around with this idea, and I came up with the simplest possible translator. And it is the identity translator. It proxies all requests, but it doesn't alter them in any way. And if it is used like a traditional translator in the Hurd, you can actually mount file systems or stuff like that by attaching translators to some node. And if you do this with the identity translator, so I'm attaching to the node mount the identity translator, and I feed it some directory as the underlying node, which is a bad name for, I would call it the input of the function. And now it behaves a bit like a symlink, so I just see the content of the directory. But there is a very important difference, because if I do an ls on this, what is happening is that the identity translator does the lookup for me. So the lookup is executed with the privileges of the identity translator, which is kind of a problem, but it's okay if I'm the one who is actually starting the identity translator. This is one of the open problems, how this kind of server interacts with the Hurd authentication model. But I think it's okay for personal translators. And I can query the word translator is attached to the node using this function, and it says it's the identity translator. And if I use it with the change root command, it actually implements change root, the Unix change root. And we have a change root on the Hurd, and it's implemented in the file system servers, and it's a bit like a hack. And this is a nice way to implement a change root, because I have an external server that provides a view on some resources, and I just start my program like ls or shell or Firefox or whatever, using this as the root directory. And it doesn't actually stop there, because now we can go crazy and we can implement an GPT translator. And by the way, these are actually implemented. They are kind of prototypes, but it works as I show it here. And I have this this translator, Hurd GPT, and I have a wrapper around it because it's cumbersome to use trans change root to set it up. But now I can just do verify, and this starts the PGP translator. And I do tar go fetch this archive over FTP from the GNU archive. And when it does that, it actually goes ahead and verifies the signature that is distributed with this tarball. And only if the verification succeeds, it allows me to open that file. Likewise, it allows me to encrypt a tarball. So I say encrypt for some address, and then create a tarball. And it actually creates an encrypted tarball. So this is stuff that you can do. Finally, I believe that virtual machines or virtualization technology like VMware or Box or stuff like that is popular because it's easy to explain. If I fire up a virtual machine and it's just like a physical machine, this is a good picture for the mind. And it's not I think it's very important to explain the operating system to the users, because it's important if we want to empower a user, we need to explain the system to the user, how it is composed. And this gets even more tricky if we start with the distributed system like the Hurd. And I have a prototype for that I want to demo. And there are two aspects to it. The first aspect is explaining how the system looked like at a global level. And the second is how to explain the relation between tasks. Okay, wish me luck. Let's see. So, nice, huh? This is actually a tree, and this is the root of the tree. And then we have /dev, and it looks a bit like a snowflake. It contains all the device nodes. And then we have /run, which is a a temporary file system. And if I mouse over it, it shows me some additional information about this. And we can see here is /servers, and we have sockets, and here is my TCP IP stack. And I first tried to do this with generating static images using graph-vids, but this completely failed because you get huge images that are hard to comprehend and hard to display. So I opted for an interactive exploration tool, and this is my prototype. And the other thing that you can do with it, and need to restart it. Okay. Oh no. Awesome. Okay. So this is my process. This is the Hurd web UI. And it's actually connected to other tasks, like, the proc server that implements the process, the concept of a process, of a POSIX process. And for some reason, it has a connection. Oh, what you're seeing is a directed graph. And you see an edge if this process has a port or handle to an object implemented by the server. So this edge says, for some reason, I don't know, the process opened def random or def random, I don't know. And so this is the proc server, this is the TCP IP stack, the local network stack, this is the root file system, this is the authentication server. And we can actually start from there to explore the system. For example, this is the terminal. Oh. And I can ask what other processes have opened the terminal by double-clicking on this. And I see that there's my shell that also has a port to the terminal, and sudo, because I started the program with privileges, because it has to be privileged to probe into all the other processes. And we can ask, what other kind of programs are using the TCP IP stack. A bunch. It's awesome what the JavaScript world can do, huh? And we see actually, here's the Ethernet multiplexer. And if I open it, it works better with a bigger display. We see it has a connection to the device driver, which is to be expected. Oh. So, to conclude, from my point of view, being able to manipulate the virtual file system is a way to do fine-grained virtualization on the Hurd. And it's actually surprisingly easy and fun to do on a multi-server operating system. And if you're interested, you should actually come talk to us, join us, do some fun stuff with it. And you can imagine all kinds of servers that do similar things to this. So maybe we can have a gigs translator, because there are people working on porting GNU gigs to the Hurd, or the other way around, or both. And Manoli sits here, and he's going to give a talk about that tomorrow. I hope that's up to date. And if you haven't already, you should go ahead and watch the previous talk, because the previous talk was about the same thing, mostly was for the G-Node operating system. And it's interesting to see their perspective on this. So if you're interested, go ahead and watch it. And if you want, there are 2 fun papers. Both are called Are Virtual Machine Monitors Microkernels Done Right? The one argues pro, the other contra. And it's a nice introduction to, different ways on the world. And that's it. I'm happy to accept questions.
So is your web server running on a Hurd machine, or is it using statically gathered data?
So the question is about the web server. It's actually running on the Hurd system. This one, by the way, Hurd is running on actually hardware. Not on new hardware, but on hardware. And it's actually gathering the information from the system. We have this thing called port info, which does the same thing, but not with the JSON interface.
Thanks for the talk, very interesting. I know almost nothing about Hurd, so maybe my question will be naive, but you compared it to Plan 9 a couple of times. I wanted to know if you are able to actually run different servers on different machines through Hurd, like Plan 9 can do, and is the PFS, I think, able to talk about the network and talk to other systems?
So the question was whether we can have the Hurd running across different machines on a network, and if it provides a single system image kind of interface. The answer is no. Mark was designed to allow that, but it was lost or never really implemented. And I know there's a guy working on net message that is able to send Mark messages across the network. And I haven't tried it, but apparently it works to some degree. I don't know. So it's possible in theory, but it's not our focus. Oh yeah, sure.
Just a speculation. I don't know too much about it either. But when SMTP support gets into Hurd eventually in the future somewhere, and don't know when, what would the impact on sub-Hurds be in terms of privileges? And I mean, a sub-Hurd could potentially hog its host. So.
Right. So the question is about SMP support and how it impacts sub-Hurds. So Mark has been always SMP capable, but currently our version of Mark only runs on 32-bit Intel processors, and we don't do SMP, sorry. And if we would, that would be nice. Then again, and the second part was about whether one sub-Hurd can hog resources like the processors.
Accounting, basically.
Accounting. We don't do accounting, and that's a huge problem. And so we don't have a good answer for denial of service attacks, basically. If you need that, you should probably look at G-Node.
I can look at Mac and implement it's better.
It's possible to implement that in Mark. Everything is possible in theory, but it would require a huge amount of work to bring Mark up to speed. Oh.
You probably wanted to avoid it, but I still ask the question, if you are talking about different kinds of virtualization, so what about some kind of hardware-assisted virtualization when you really need, for some reason, I don't know why, to run a different OS image?
So the question is whether we want to use hardware virtualization if we want to run a different operating system. And sure, if we want to do that, we should port QEMU and stuff like that. Someone would have to do it. I'm not that interested in that, because I think this is more fun.
Yeah, but from the architectural point of view, where would the hypervisor reside? It would be it would be an extension to the Mac kernel, or it would be a user space component, or is there some road plan for that?
So the question was whether it's possible to implement that in the kernel or maybe also in user space, a hypervisor. I'm not sure. We do device drivers in user space, so maybe it's possible to implement some or most of that in user space too. I don't know.
Yeah, regarding the two papers, are virtual machine monitors microkernels done right? Don't you think Heiser is in a better position because he can refer questions to his colleague and probably co-worker with the words "talk to the hand"?
So this was a snarky remark about the papers and one author being named Hand, so the other one can say talk to the hand. Lots of fun papers, you should read them. It's about mostly about Zen, and the first paper argues that Zen is a better way to approach the problem because of this and this, and the other paper refutes these claims by interpreting the Zen architecture from a microkernel point of view, and it's a fun read.
So which paper was published or written first? Do you know?
Yeah, the first one. And this is from the Zen people, and it's pro, and the other one was written later, and it's contra. All right. Any more questions? I guess not. Then, thank you.